No question.
Sorry, we can't hear you.
Can't hear me.
No, we can't.
We can actually. He posts.
Yeah.
Yeah, because I have tested. I have two devices, and on one I can control that. Basically, you can see me, and the echo in the beginning that was meaning that the sound. That's not my fault. Maybe it's somewhere in between. Okay. So, any questions? Okay. It's pity because you've missed your opportunity to ask your questions. I remind you that you have all home assignments posted, all past exams posted. So if you basically can solve everything, then you are free, do what you wish, and be happy. Okay, so let's solve some more or less difficult problem on stochastic integration, on properties of stochastic integral. Let me find it. Okay. Okay, basically exercise. I have a process xt that is TWT. WT always denotes winner process. So we will often use it. So I will not even say that WT is winner process. TWT plus integral from 0 to t UWU squared DWU. So my first question is find dxt, check whether xt is a martingale. Second point, find expected value of xt and variance of xt. So basically, that's the first exercise I would like to solve. Just I will give you, let's say, because I would like that you make all the work, and I just I prefer to answer questions. So I give you, let's say, 2 or 3 minutes to find dxt. So just 2 minutes. 2 minutes for you to find dxt, and we will discuss the result in 2 minutes. Just open your notes or any web sources on ETAS process. And just find dxt. Okay, any, 1 minute remains, 40 seconds, I think. Any results? Have you succeeded to find dxt? If you will not answer, just answer no, yes. If you don't answer, I will finish our class. It doesn't work like this. You just say no, I can't. I don't understand. Just, it's not difficult to answer in chat anywhere. It's okay, but be active. the answer no, I don't understand is okay. Okay, Evgeny, yes. So what's the result? If you have mastered, what is the result?
I got Wt dt.
So dxt equals to
Wt dt
Wt dt. Okay.
Plus plus t dwt.
Okay.
And plus the integral, I think.
No.
I don't know what to do with this integral.
Okay, but 1/2 you have perfectly done. Yeah, 1/2 this part is perfect. Okay, but okay, anyone has mastered to work with integral?
I think the integral part, I am not sure if I'm very correct. My part was uw squared dt.
Uw squared d.
Sorry, dwt.
Yeah, you are completely right. It's dwt squared dwt. Yeah, yeah, that's
Okay.
perfect.
And can you please, I understand the first and third term, but can you please evaluate on the second term?
Second?
Of t, t dwt, yeah.
Okay, I have used two ideas during this exercise. First idea, that when you write, you have a full form. I don't know, integral from 0 to t hedgehog u du plus integral from 0 to t elephant u dwu. In shorthand notation, if you have some process mt, then dmt will be hedgehog t dt plus elephant t dwt. So with the second term, I see that an integral. So in shorthand notation, so I'm just asking for shorthand notation. So this will be transformed into the last term. Okay, so it's just a shorthand notation. In full form, we have integral. In short form is meaningless by itself, but we have just we drop integral, we replace index by t, and basically we are done when we write short form instead of full form. Okay, and for that part, I will use Ito's lemma. Ito's lemma says that if we have a function, and here we obviously have a function of t and wt, that is just t times wt, it's our function, yeah. And Ito's lemma, the simplest one, states that we need to take f prime with respect to t plus, so df will be f prime t dt plus f prime w dwt plus correction term 1/2 f prime prime ww times dwt squared. That is equal according to meaningless by itself agreement, but it has a full form honest expression, so it's, let's say, equal to dt. Basically, in this case, if I take derivatives of this function with respect to t is, so basically this is that part, because second derivative with respect to ww is 0, okay?
Yeah, okay, I just forgot about this and tried to imagine something.
So, okay, basically that the properties of a short form notation and Ito's lemma. I have used two ideas. So basically dxt is what is t dwt plus wt plus twt squared times dt. Okay, so now we have a short form expression for dxt. So xt is a ethers process, is an ether process. So we can state that xt is x0 plus integral from 0 to t u dwu plus integral from 0 to t wu plus u wu squared times du. Okay, we see that xt can be represented as a sum of two integrals, as many continuous time, as many continuous stochastic processes in continuous time. And basically, we have completed the point. So now the next question is very easy, because we have a theorem how to quickly check whether an ethers process, whether it's a martingale or not a martingale. Our xt, is it a martingale or not? It's very easy. You just look and say, oh, it's a martingale. Oh, it's not a martingale.
No.
Ch is right. Yeah, you are completely right. Ch is no. Why it's not a martingale?
Because there is a part with dt. Exactly.
There is a part with dt in a short form, or there is a integral, Riemann integral in full form. So that part prohibits my process to be a martingale. So xt is not a martingale. Xt is not a martingale. Okay. Now we can find expected value of xt and variance of xt. Let's go on. So I give you, let's say, 2 minutes to find expected value of xt. With variance of xt, it's a little bit more tricky. I will help you, because expected value is more or less easy, but the variance is the hardest point in this exercise, I think. But if you can, you should try at least, yeah. But I warn you that expected value is easy. You just look at the properties, and variance is a little bit tricky. So it's tricky, and that one is easy.
I'm sorry, can you scroll up a little?
Yes, I can.
So wait here, a little bit up, and a little bit more. So I wanted to ask, here's the third term is twt squared dwt. And then we write, exchange dwt for dt here in the lower.
Sorry, f prime.
Here. And I'm a little bit confused.
I forgot something. Yeah, I forgot. Yeah. You are right. Yeah. I missed. Yeah. It's my fault. Yeah, you are completely right. So I have two terms with dwt, t plus from 0 to t, u plus uw squared times dwu plus integral from 0 to t, wu dwu. Yeah, like that. But the answer here stays the same. So this one, the term with du is present, so xt is not a martingale.
Посмотрим, нет, или продолжим, или ты пока так это поняла, что делается?
Ну, я поняла плюс-минус. I'm sorry.
Yeah. Have fun. Okay. Any questions?
Can you? Yeah. Thank you.
Okay, we continue. Can we continue?
Thank you. Yeah, thank you. I understand.
It's not for you, it's for everyone. Just say yes, no, just be active.
Yes,
It's
yes,
okay
yes,
when you
yes,
say,
yes,
I
yes.
don't understand. It's okay when you say no, just stop. It's okay. It's fine to say no, I have questions. It's fine to say yes, I have no questions. But it's a bad strategy to be completely silent. It's not so hard to, even if there is, I don't know, a lot of noise, you are in a pub, in a nightclub, I don't care, but you can type plus or minus in the chat. I have a lot of opportunities to interact with me. Voice, chat, everything is fine. Okay, so what is expected value of xt? That one is easy. It's for Stepan, it's for expected value, your attempt, t squared. I think no, just let's try expected value of xt. I just plug in what I know about xt. What I know about xt, it's twt plus integral from 0 to t uwu squared dwu. Okay, what's random in the first term? So what's random here? What's random in the first term?
Do we have?
Sorry?
I'm not very sure. So let me just wait.
What is random in the first term? In this twt, what is constant? What is random?
WT
Yeah,
is
Stepan,
random variable.
Yeah, WT is random variable. So I can write t times expected value of WT plus. And what is expected value of, I assume that my assumptions hold. So I will not check them. But I have expected value of stochastic integral. And under mild technical conditions, stochastic expected value of stochastic integral is sorry,
0.
0. Yeah. So it's like an easy question. Yeah, just pop. And that guy is 0. That guy is 0 by the properties of Wiener process, and we have 0. Okay, it's a little bit trickier with variance. Variance is, let's say, not so easy, but okay, let's go with variance.
Sorry.
Yeah.
The second term is 0 because there is a property.
Yeah, because of a property, because stochastic integral is a martingale. Intuitively, what is a stochastic integral? You invest in a Brownian motion. Brownian motion has normal independent increments. So when you invest in a Brownian motion, you buy 5 Brownian motions, so you sell 5 Brownian motions. Future change, in the future, Brownian motion can go up, can go down with equal probability. And future changes of Brownian motion are independent of the past. So if you have bought a lot of Wiener process, 5 shares of Wiener process company, it will go up with probability 1/2, it will go down with probability 1/2, so your expected profit is 0. Okay, yeah, it's a property of stochastic integral under some mild technical condition that something is bounded, but intuitively it's clear. From mathematical viewpoint, there are some conditions that should be checked, but we will not check them. We have only 6 weeks for the whole stochastic calculus course. We cannot have all mathematical rigor that can be in this course. Okay, so what about variance of my xt? What?
Boris Borisovich, I wanted
Yeah.
to ask, when
Yeah.
calculating expected value and variance, does it matter if we use the xt that was given or the xt that we have found?
No, it's the same. It's
It's
just
the
another
same.
representation. Yeah.
So we choose the one that is easier to calculate, right?
Yeah. Obviously. Yeah. You choose that. With the second one, it's also okay. So if you have a, so let me work with the second one. It's also okay. So yeah, both expressions are correct. So it's like 4 is equal 2 plus 2, 4 is equal 5 minus 1. You can use any expression you wish. So I can work with that one. It's okay. Yeah. I just remark that x0 is 0. Yeah. If you look at this process, where it is, if you look at this process, you can remark that x0 is 0. Just place t, instead of t, you place 0. So you have initial condition. And according this expression, it says that expected value of xt is 0, starting value, plus 0, because it's expected value of stochastic integral, plus in Riemann integral, expected value goes inside integral. And you once again obtain 0. So basically the answer is the same,
clear,
because these are just two representations of the same process. Okay, what about variance? Variance is a little bit trickier. Variance of xt. So I will use the first representation, twt plus integral from 0 to t uwu squared dwu. Okay, it's variance of the first term plus variance of the integral plus 2 covariances of the first term with the second one. Okay, let's tackle them by one by one. First one is easy, so I will put semicolon there. Variance of twt, just take out t squared because it's non-random. And what is the variance of wt?
That's t.
Yeah. T squared times t, it's t cubed. Okay, 1/3 is done. Okay, let's recall some properties. What is the variance of stochastic integral? We have a property that says, what is the variance of stochastic integral? Last lecture, we have introduced properties of stochastic integration. We have not proven them, but we can use them for free.
It's an integral of the expected value of uwu squared.
Yeah, you're completely right. It's expected value of uw squared. We should add square there and take ordinary Riemann integral. That's fine. Have you found this property?
Yes, we did.
Okay, thank you. Just answer about, I advise you, when I ask, have you found, I mean, you, so you, that means you can answer for yourself. Don't care about those who are too shy to answer. So if your strategy is to be silent, I don't approve it, but it's your choice. Okay. You have opportunity to talk, but if you'd like to be shy, okay. Expected value 0 to t, expected value of u squared w power 4 du. Last lecture, we have calculated expected value of w to the power 4. So it was integral from 0 to t u squared. And what was the expected value of w to the power 4? Just
it was
look.
3t squared.
Yeah, it was 3t squared. Okay, 3u squared du. So it's last lecture. Okay, and finally, I have 3t to the power 5 divided by, I think, by 5. Yeah. Any
Yeah.
question? We can continue.
But we
Yeah.
don't care about constant here, right?
Which constant?
When we usually do some integrals.
Yeah, you do.
Okay. Yeah. No mind. I mixed something up. Yeah.
We care, but it's 0.
Yeah.
So the answer
I
is
forgot
not
that
we
the
don't care.
last limit
We
was.
care. We are careful, but it's 0.
Yeah. Thank you. Sorry.
Okay, and the last, the most tricky one, I think we need to find covariance of TWT with a stochastic integral from, oh, I don't remember, UWU squared DWU. Yeah. Okay, T is non-random, so we just move it out. Covariance WT UW. Okay. Now, what is WT? WT can be, so basically the main idea that a lot of processes can be represented as a sum of two integrals, okay? And Brownian motion itself can be represented as an integral, yeah? So we just will represent, this WT as an integral. If you buy just one share of winner process company, and then your initial welfare is 0, your final welfare is WT, so the integral is WT. So if you just buy one share of winner process corporation. And now I have transformed winner process into it as integral, and I have a property that allows me to calculate covariance between two integrals. How do we calculate covariance between two integrals?
It will be integral from 0 to t, expected value of multiplication of these integrals.
Yeah, I just multiply 1 by u by w squared du. It will be t times integral from 0 to t u times u du. Yeah, it will be t times t cube over 3 minus 0. Yeah, and it's t to the power 4 divided over 3. Okay.
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 So basically, I think we have found everything we need. So the final answer is just a sum of these 3 terms, like so basically we can write the final answer. So variance of xt just t cube plus 3t squared over 5 plus 2 times t to the power 4 over 3. I think everything is completed now. Okay.
Okay.
Yes.
Yes.
Now let's go on and work a little bit with Gersanov theorem, because it's a little bit hard to to fill. So let's move on to Girsanov theorem. We have already seen during our work with martingales that sometimes you can change probabilities. If you recall, we have studied a process that was not a martingale, but we have changed probabilities, and it was a martingale after the change of probabilities. So if you remember, it was a process, but basically that's idea is in discrete time, the idea is trivial, but in continuous time, it's hard to prove. It's a theorem with a name. Yeah, it's not so easy. But in discrete time, the idea is very simple. So if you have some a random variable x, and that with values x has let's say value, or I will provide you an exercise to show you the idea of Girsanov theorem. Values of x are let's say let's say they are 0, 1, and 2. Yeah, and and here probabilities are just a moment. Just a moment. Probability that x is equal to a. Let's say probabilities are probabilities are 2 alpha, alpha plus 0.1, and 0.9 minus 3 alpha. Yeah, like this. Probabilities are not specified completely. 2 alpha, alpha plus 0.1, and 0.9 minus 3 alpha. These are honest probabilities because they sum to 1. And my question is find alpha such that expected value of x is 1. So my exercise is very simple because in discrete time, the idea is very simple.
It's 0.
0? No.
It's 0.1.
0.1, yes.
0.1.
Yeah.
Yeah, because you should have 0 times 2 alpha plus 1 times 0.9 minus 3 alpha plus 2 alpha plus 0.1 should be equal to 1. Yeah, and then if you just simplify and solve that, you will obtain something like alpha is 0.1. Yeah?
Yes.
Or you can just reason by symmetry argument. Probability of 1 does not matter. What you should have is symmetry between 2 alpha and alpha plus 0.1. So by symmetry, you can just say 2 alpha should be equal to alpha plus 0.1, and the alpha is 0.1. But you can honestly calculate okay, but it's okay. It's an easy exercise. In continuous time with not one random variable, but a lot of random variables that are interlinked between them, it's hard to prove such a theorem. So let's state, at least without proof. So imagine that Girsanov theorem. So imagine that you have WT, that is a winner process. Winner process with respect to filtration FT under probability measure under probability measure P. And the WT star is equal to WT plus alpha times T. So WT star is just WT plus alpha times T. And Girsanov theorem says that there is another probability measure P star. That's just another probability, another way to calculate probabilities, such that WT star is a winner process with respect to filtration FT under probability measure P star. Okay, let's try a little bit to work with this strange statement about changing probabilities.
Let's work.
Yeah. Exercise. So we start that WT is a winner process with respect to filtration FT under probability measure P. We have WT star that is equal WT plus, let's say, 2T. According to Girsanov theorem, there exists probability measure P star such that WT star is a winner process with respect to FT under.
This is such that this is star, right? It's not a, like tick or something. Yeah. Yeah. Okay.
Yeah, we have a star like that.
Thank you. Very beautiful.
My question is, so when you have two probability measures, you can calculate expected value variances according to one probability measure. You can calculate probabilities, expected value and variances according to other probability measure, because if you change probabilities, expected value will also change, yeah, because expected value is calculated using probabilities. So you have expected value and expected value star in this problem, variance and variance star, okay? And my question is to calculate probability that WT is greater than 0, probability then WT star is greater than 0, probability star then W star is greater than 0, let's say 1, let's say 1. Let it be 1. Yeah, let it be 1. And probability star that W1 is greater than 0. Calculate expected value of W1, expected value of W1 star, expected value star of W1, expected value star of W star and W1, variance of W1, variance of W1 star, variance star of W1 star, variance star of W1. I think that's more or less enough, but you can calculate something like, if you just like to do something more, you can just calculate something like expected value of W1 times W2 star, or expected value star of W1 W2 star. So just any combination is okay. So in this exercise, you have many probabilities, not so many, 2 probabilities. So you have 2 different ways to calculate variances, 2 different ways to calculate expected values, 2 different, basically everything has a star companion, and the answer in general is different. It may coincide sometimes, but in general, the answer is different. Okay, let's do it. Yeah, the question is clear.
Yes, but may you please for a second scroll up to Gersonov theorem? Like first, yeah. This is VT plus arbitrarily alpha T, but here in our task it's stated, okay, thank you.
Gersonov theorem says that for any alpha, so obviously this probability star depends on alpha. For alpha equal to 2, it will be 1 probability star. For alpha equal to -5, it will be another probability star. So yes.
Okay, thank you.
Yeah, it is.
Sorry, what does it mean that WT is winner process under probability measure? So I couldn't understand it.
Just 5 properties of a winner process hold if you use probability measure to check them. Because, for example, the property number 3, what is the property number, let's say, I don't remember the numbers, but in so in properties of a winner process, there is a property, I don't remember the number, that expected value of difference WT minus WS should be 0, yeah? Because one property says that this difference has normal distribution, yeah?
Linus, property 4.
It's not important for me. Property 4, 45, I don't care. There is a property. I don't remember the numbers. They are not just renumber them. It's a crazy thing to learn numbers. The main idea is to learn properties, not the numbers.
Mm-hmm.
Okay, and this obviously depends on the way how you assign probabilities to events. If you assign high probability for big value of WT minus WS, then your expected value will be high. If you assign low probability to high value of this difference, then your expected value will be lower. So expected value of this difference depends on the way how you assign probabilities. Okay? Okay,
thank you, I got it.
So let's go on. What is the probability that W1 is greater than 0? But according our exercise, W1 is has normal distribution with mean 0 and variance 1 on the probability measure P. Yeah. Okay. It's
Yes.
this statement of it. It's given. Yeah. So what is the probability that W1 will be greater than 0?
Is 0.
0.5.
Yeah, it's 1/2. Yeah, you're right, because it's symmetric around 0. I don't care about variance, but it's symmetric around 0. Okay, now what about probabilities that W1 star is greater than 0? What is W1 star? W1 star is W1 plus what? Plus 2 times 1. And its probability is that W1 will be greater than -2. If you remember, so I will not check normal distribution table, but just one number that is worth remembering, that the probability that normal standard random variable is from -2 is 2, from -2 to 2, that probability is 95%, okay?
Yes.
So for a standard normal random variable, this probability is 95%. It just helps you to calculate confidence intervals intuitively faster. Okay, so what's this probability is just roughly 0.975, yeah, because we have 2.5% to the left tail and 2.5% to the right tail. Any questions?
Clear? No.
Okay, we go on. The next one is easy. The next one is, it's your turn.
0.5.
Yeah, 0.5. Yeah, the next one, probability star, that W1 star is greater than 0, but W1 star has normal distribution with mean 0 and variance 1 under P star. That's the statement of Girsanov theorem. W is a winner process with respect to P. W star is a winner process with respect to P star. So when you calculate properties, expected values, variances, anything, when you work with W star, if you use P star, oh, I have a winner process. If you work with W, you use P, and you say, oh, I have winner process. Yeah?
Yeah.
So it's 1/2. Okay, what is the probability star that W1 is greater than 0?
0.025?
Yeah, I think yes, because we can say like it's W1 star -2. So it's W1 star greater than 2. But according to Girsanov theorem, P star and W star, they have a perfect match. W star is a winner process with respect to P star. And then it's basically 0.025. Any questions here?
No questions so far.
Okay, so it's up to you to calculate all that for guys. I give you, I think, 3 minutes. 3 minutes to calculate all these 4 expressions.
agree
Yeah,
with
I think
Evgeny.
is right.
Yes.
Yeah, I
Yes.
think Evgeny is right. When we have a match, then the answer is easy. This is 0. This is also 0 because we have match W and expected value without star, W star and expected value with star. So we have a perfect match. Two other cases are a little bit more difficult, but not so much. So we just say it's easier to change inside expected value. So we just say that it's W1 plus 2, and it's 2. And here it's once again, it's easy to change inside the expected value. So it's started expected value of W1 star minus 2, and it's minus 2. Okay?
Okay.
Yes.
Yes, yes.
Okay, and the last one with variances. So just finish the exercise. Just finish the exercise.
As for variance, wouldn't it be just once for all of them?
Yeah, okay, I agree. Variances will be 1, 1, 1, 1, 1. Yes, I agree. Variances will be 1, 1, 1, 1, 1. Yeah, if you have any questions, if something is not clear, then just don't be shy and ask. Because I like that you work during classes and not me. I can answer questions, discuss your solutions or proposals, ideas.
Can you explain, please, why variance of the mixed examples is also 1?
Okay, like with the case, like in the case with expected values, it's easy to change inside because there are infinite number of events, and it's difficult to describe all probabilities, because probability measure, you need to discuss how to change, how the probability is changed. So I will just deal with that one. So it's variance of W1 star. I replace inside variance is W1, what is definition of W star plus 2. But variance is not affected by a constant inside. So just variance of W1. Now I have a perfect match. I have variance without star. I have W without star. So W is a winner process. I can check just the definition of winner process, and it's 1.
Yes, thanks.
Okay, and point D.
Well, I got to the point of expected value of the multiplication of W1, W2, and now I'm trying to do something further.
Okay, let's solve one of them. What is the expected value of W1, W2 star? It's expected. Once again, it's difficult to change E. Yeah, it's easier to change inside. Yeah,
yes.
Main point. Because to calculate, we will use this trick. Basically, why do we need it? Because it seems some strange exercise. We have changed probability. Now we have different expected value, different variances. So it's more or less intuitively clear. Yeah, when you change probabilities, expected value. Values
well.
do change. Yeah, that's nothing counterintuitive. Yeah, W2. I think plus 4, yeah, because it's
yes.
expected value of W1, W2 plus 4 W1. It's expected value of W1, W2 plus 4 expected value of W1. This is 0.
Yes.
So I have expected value of 1 W2. Once again, I can say that this is like covariance of W1, W2. Yeah?
Yeah, I agree.
Because expected value is 0. And I think we have, when we studied winner process, we have discussed covariance between two. As far as I remember, we have found covariance of WT and WS given S is before T on the timeline.
Yes, it was S.
Yes, it was S. So in our case, it's
It's 1.
Yeah, because
Yeah,
T is
thank
2
you.
and this is 1. And I think we need to solve the last one. Expected value star, W1, W2 star. Expected value of W1 star plus, no, minus 1, I think. No, minus 2. WT star, W2 star.
Yeah.
And it's expected value of W1 star, W2 star, minus 2 expected value of W2 star. And then it's covariance of, covariance star, yeah, covariance W1 star. I've missed star. I've missed star on every expected value because they're different. Yeah, should be careful.
We didn't want to interrupt you.
Yeah. Yeah, any questions?
No. It will be 1 as well.
Yeah, in this case, the answer does not change whether we use expected value or expected value star, but sometimes it does. Just my point that sometimes it's changed, sometimes it's the value is preserved. Okay, and I think we have time for one more small exercise. For 5 minutes. Just if you have any questions, just don't be shy. But if you have no questions, just a small exercise to have a little bit more practice. Oh, yeah. Let's. A good exercise. In a Black-Scholes model, you have DST equals to mu st dw dwt plus sigma st dwt, and we have let's my question is, let's introduce yt, that is logarithm of st, and my question, find dyt. That's question A, and question B, find st explicitly. So what is dyt? Yt is a function of an iter process, so I use the second version of iter's lemma, more general one. It says that to calculate dyt, I need to take the derivative with respect to s. It would be 1 over st times dst plus 1 over 2. What is the second derivative with respect to s?
We have 1 over st squared.
Minus 1
1
over
over st squared.
squared dst squared.
Mm-hmm.
And I recall that this is pure nonsense. It has no meaning by itself.
Mm-hmm.
The only goal of this expression is to simplify it using rules like dt times dt is d0, dwt squared is dt, dt times dwt is 0. So we'll simplify it and recover the full form. Okay, let's simplify it. I will just plug in dst. I will plug in dst there, and I will plug in dst in the last term. So dyt is st will disappear, so it will be mu dt plus sigma dwt, first term, minus 1 over 2. What is dst squared? It will be mu st dt plus sigma st dwt squared. Will be mu dt plus sigma dwt minus 1 over 2 st squared. What will happen there? dt squared will disappear. dwt squared will be dt. So I have sigma squared st squared dt. And dt times dwt will also disappear.
0. Mm-hmm.
It will be sigma dwt plus mu minus sigma squared over 2 times dt. And so basically yt is y0 plus integral from 0 to t sigma dwu plus integral from 0 to t mu minus sigma squared over 2 du. I can take all these integrals. That says ln st is ln s0 plus sigma times wt plus mu minus sigma squared over 2 times t. And finally, I have st is s0 times exponent of sigma wt plus mu minus sigma squared over t over 2 times t. Alexandra is right. I haven't noticed in the chat the correct second derivative. Alexandra is right.
I'm sorry.
Yes?
No, that's okay. You just like, I understood. Yeah.
If you have any questions, just tell me the number of line.
Oh, sorry, could you comment on the fifth line?
So it's the definition of y.
Okay, clear.
So y was defined as a logarithm. What is the value of this integral? Is just a constant. Yeah, it's a constant. The integral of a constant is a constant times t. Yeah.
Yeah.
And here we interpret like we have sigma shares of Wiener Process Corporation. At the beginning, the worth, my wealth is 0. At the end, I have sigma shares of Wiener Process Corporation. and their price is WT. So my welfare at the end is sigma shares times the price WT. Okay.
Can you please explain the second line? What is between the brackets and why is it so?
What is between brackets?
Yes, yes, yes.
Use
So
use these rules. This term square. So when you have a plus b squared, it's a squared plus b squared plus 2ab. Yeah. This term squared would give me mu squared s squared dt squared.
yes,
But dt squared is
is 0. Ah,
0.
okay. Yes, now I get it. Thanks.
So when I square mu, I get mu squared. But when I square these terms, I have 3 rules to work with them. Okay, basically that's all for today. We have solved some exercise just for practice, and the next time we will introduce Girsanov. We will use Girsanov theorem to solve to find the price of European asset in Black-Scholes model. So now we have just introduced it and played a little bit with it, and next lecture, we will use Black-Scholes model to we will use Girsanov theorem to find the price of an option in Black-Scholes model.
And can you please briefly tell what should we do when we ask to find ST explicitly?
This is explicit form.
Yeah, it's just I thought
that means
I thought maybe
formula.
We'll continue with G. Yeah, never mind. May I ask you about, not clearly about homework, but homework related question. I just want to understand if I do really understand correctly. So when we have a fair dice, for example, and we have 2 independent throws, our sigma algebra will contain 2 in the power 36, right?
Sorry, how many? What's your experiment?
Fair dice, so 1 from 1 to 6. And 2 throws, it will be 2 in the power 36, right?
Yeah. If you observe, all the result without loss of information, so maybe if you live in a Pirahu tribe, then you can't count more than 2. You can just count 1, 2, and many. So if you are from Pirahu, then your sigma algebra will be smaller. So it depends on sigma algebra depends on what you observe. So you throw a dice twice. If you are a rational girl you can see all the results. You can distinguish between all the numbers, and then yes. But if you are from Pirahu, then your sigma algebra will be smaller. So it depends on your what do you observe about these tosses. It does not only depend on the experiment, but it depends on your information. Maybe you have tossed the coin twice, but you were in the other room. So your sigma algebra in this case will be empty set and full omega, because the coin is tossed twice, but you do not see
the result.
In our home assignment, do we suppose to have always a fair coin and a fair dice? If not specified otherwise, then yes.
And also about first one, we are told that you observe the results of 10 independent coin tosses. So we just with our sigma algebra, we can tell what the result is.
Yeah.
Okay. Thank you.
Boris Borisovich, I wanted to ask about Black-Scholes model. So in the past exam collections, there are a lot of exercises on finding the price at some time. So this is what we'll do at the next lecture, right?
Yeah. Or maybe next class.
Okay. So we should not use Ito's lemma there. It's useless to try. Okay, I just will wait till next.
Just wait. Wait.
Okay.
We will solve. We will find the price of European contract in the Black-Scholes model. Okay, bye-bye.
Thank you for the class. Bye.
Okay, thank you.
Thank you.
Goodbye.
Bye.